Let's go back to the case where there is one central server and multiple different worker nodes. Okay. For this scenario, each worker node compute the mini-batch gradient, and then the gradient vector will be reported to the central server every iteration. So when there are 100 or 1,000 different worker nodes, then every iteration you have to communicate 1,000 times with the central server and one single worker node, because there are 1,000 different worker nodes. That is huge, right? So people think this huge communication is kind of bottleneck or some very waste of your resource. So one possible solution for this is let's rarely communicate with the central node. So instead of communicating every time, let's communicate every 10 iteration or every 100 iteration. I mean, don't send the gradient vector right after every iteration. Keep the SGD update locally several times, and then just rarely update the information to the central server. Okay, so let's say the frequency is every 10 iteration. Then how can operate? At time t0, all the nodes share the same. So x0, the first node, x0, second node, every node share the same vector. But at time 1, x1 will be updated using local gradient. Every server independently. So now the equality will broken 1,000. So you run this iteration 10 times. So after 10 times of update, each worker node will have different information, right? And this information will send to the central server, and the central server will combine all the information, just take the average. Okay, just take the average. And broadcast the average information to all the local server. So now the updated information will share the same value again. So from time t10 to t20, we repeatedly run the same procedure. Every local server run the SGD independently, and then send the last time information to the central server, and the central server just combine all the information by taking average and then broadcasts the averaged information to all the worker node. That is local SGD. So to study the local SGD theoretical convergence behavior, we have to take into account the mismatch between local server, the worker node, during the inner loop update. Okay, so from T0 to T10, every local server, local node, they just update their local parameter without communicate, right? So during this slot, the average gradient, essentially, the gradient computed from server 1, I'm using the G tilde 1 and G tilde 2, they compute the gradient at different point. Okay, so now even if you take the averaging between whole node, the expectation of the averaged gradient is not unbiased estimator, because the point you take the gradient is different. Server 1 compute the gradient at different point. Server 2 also take the gradient at different point, and so on. So there is additional error, some additional error, or noise due to this fact. Okay, the mismatch between work-on nodes could introduce additional noise. So we have to take into account this additional part. Okay, so this paper very well analyzed this convergence behavior. Not this paper, sorry. This paper, tighter theory for local SGD on identical and heterogeneous data. This paper assumes some strong convexity and L smoothness and some bounded variance term and some bounded variance for the sampled node or sample data point. And then under this assumption, they provide convergence behavior, convergence speed of local SGD algorithm. So here the H is the interval between two to the cumulative action, the central communication. And as you use more higher H value, there's one additional term here. One additional term when you look at the theorem 1, there's one additional term, this term, and this additional term increase as you increase the interval H. Okay. So when you look at the proof, they basically analyze the difference between the local server's parameter value. They compute the expected difference at every iteration, and based on this, they analyze the convergence speed and convergence error. And when you look at the proof, you can easily notice that this additional term, the additional error because of the long-term update interval, generate such term. So when you use totally centralized update, so every worker node send gradient immediately to the central node, you only have this term. Okay, and when you look at this term, this also have a sigma squared, the stochastic gradient variance term, but the variance will be decreased as you increase the number of server m, and with it proportional to 1 over m. That is very typical thing. So when you take the sum random variable, then the averaging can reduce the variance, and because of that fact, we can get better convergence behavior as you increase more servers. As you employ more server, you can decrease the variance, but it naturally increases the communication cost. So to reduce the communication cost, you can learn the local SGD algorithm, but to reduce the communication cost, you have to increase the interval size h, but the interval size h could generate additional error due to the mismatch between different servers during the update rule, and it proportional to the size. Okay, right, all right. So there are many theoretical papers analyzing the local SGD convergence behavior, and one main very interesting question is really local SGD algorithm perform better than mini-batch SGD algorithm. So what this mean is um, when you learn local SGD algorithm, you just learn SGD update locally several times and then update the information to the central server with H interval. But you can also implement very simple algorithm that just simply increase the mini batch size. So do not learn several SGD update rule locally. Just take the very long mini batch gradient computation. Okay. So benefit of this part is this algorithm can update parameters several times, which usually good sign. But one bad side of this algorithm, this part is because you do not report the gradient to the central server every iteration, you have some mismatch between local servers, and it introduces additional error term like the reference paper. This algorithm, because you use a very large size of mini batch, you can decrease the variance sigma square using this increased mini batch size. So, and also because you do not introduce any mismatch problem, because you every time you update, you report your gradient descent update to the central server, so you don't have such additional term. But the problem is you update parameter very rarely. Okay, you just update one time. Okay, that is one caveat of this approach. Essentially, it is very difficult question which one is better than the other one. Okay? And this paper, very recent paper, provides very elegant theory where the paper analyzed the very tight conversion speed of local SGD algorithm, and they provide one example where local SGD performed better than mini batch SGD theoretically. And also they also provide some other examples where mini batch SGD algorithm performs better than local SGD algorithm. So in conclusion, it is very difficult to say which one is better. Okay.